guys, in this video we're going to be talking about electrolytes. At the end of this, you should know what substances are strong electrolytes, weak electrolytes, and non-electrolytes. You should be able to know what an acid and base is and identify them as either strong, weak, or non-electrolytes. Also, you should be able to define and give example of electrolytes. So let's start with a quick overview of what the properties of water are. So water is polar. So again, just from reiteration from the last video, polar substances are going to be able to dissolve other polar substances, and they're going to be able to dissolve ionic substances. So when we have a polar substance, it's going to have a greater electrostatic forces than in nonpolar substances. Specifically, we have partial charges. And those partial charges are going to like other partial charges, or they're going to like full charges, and they're going to be attracted or repelled by those charges. As a result of these partial charges, things are going to be held together better, right? They're going to be more attracted to each other. So they're going to have higher boiling points, and so higher boiling point for water than other similarly massed things. And another thing that occurs because of these electrostatic forces within water is that water is less dense in the solid form than in the liquid form. Which is why ice is going to float on top of water. So I'm just going to zoom in real quick on here. So this is what a water molecule looks like. It has a dipole, which we're going to talk about more later in this, not this unit, but in a later unit. But basically what happens is we get a partial negative charge and a partial positive charge on our molecule, and it acts kind of like a little baby magnet. All right, so you can see that kind of magnet type of nature up here. So we've got a positive end that acts like a little north pole and a negative end that acts like a little south pole. And those are going to be attracted to other poles of magnets. So positive will be attracted to negative, negative will be attracted to positive. So they're going to hold together kind of like a magnet would, which is why they hold together so much better and have higher boiling points. And anything that has little magnets, little charges in it are going to be, for the most part, soluble in water, such as an ionic compound. Ionic compounds, when they break apart, they form actual ions, and those ions are going to be very attracted to the water molecules. So here we have a full crystal of sodium chloride, and what happens is the water molecules, their little negative ends and their little positive ends, are going to kind of pluck off little parts of these ions, little sodium ions and little chlorine ions. So the sodium ions are going to be pulled off by the negative end of the water molecule because it has a positive charge, and then the chlorine ions are going to be pulled off by the little positive ends of the water molecule because of its negative charge. And it's going to do this ion by ion, pulling off these. And what happens is, even though there is a greater electrostatic force between the full positive and the full negative of the sodium and the chlorine, because of all the water molecules that can surround the sodium and chlorine ions in these hydrated spheres, it's actually more energetically favorable. So as a sodium ion breaks down, as it is dissolved in water, it's going to break down into ions that are dissolved. So 1 mole of sodium chloride produces 2 moles of ions. 1 mole of sodium ions, 1 mole of chlorine ions. Okay? This is going to be different than what happens when we dissolve a covalent compound, such as sugar. So what we have up to the left is a sugar molecule, and again, the water molecules, their partial positives and partial negatives are going to interact with the sugar, which is another polar substance. So it's also going to have partial charges, not full charges. But as the water molecule comes in and interacts with these sugar particles, these are full sugar molecules. So we're not breaking down into ions like we do with an ionic compound. So sugar will go from a solid state to an aqueous state, but it will not break down into ions. So with our ionic compound, we're breaking ionic bonds to form these solutions. With our covalent compounds, we are only breaking intermolecular forces, electrostatic forces. So to form a solution of sugar, we break electrostatic forces, weak ones, to form the solution. Remember, to have a solution, we have to have our solute completely dispersed, so we can't keep that crystal sugar together. It has to break apart into sugar molecules. But here, making a solution, we break ionic bonds. Okay? So they're very different, even though they both result in a solution, an aqueous solution, they are very different dissolving processes between an ionic compound and a covalent compound. So when we think about ionic compound breaks down into ions. So it breaks into ions in water when dissolved. They are going to have what are called charge carriers now because they're ions. Now there are charge carriers. Right, we have positive and negative charges. They can move charge. So they are going to have the ability to conduct electrons. So this gives ionic compounds the ability to conduct electrons. Okay? So, ionic compound in its solid form cannot conduct electricity because it does not have charge carriers. They are stuck in a rigid arrangement. You have to have a ability to move charge to have a charge carrier. So it has to be able to carry that charge. If you do not have an ability to move the charge, you do not have a charge carrier. In the case of ionic compounds in solid, no charge carriers. In the case of it in the water, when we have ions that are mobile, then we have charge carriers and we have the ability to conduct electrons. If we have a covalent compound, with the exception of acids and bases, we'll hit on that in just a minute, but covalent compounds don't form charge carriers when dissolved in water. So they don't break down into ions. So they don't have charge carriers. As a result, they can't conduct electrons. Okay? So why do we care? We care because if something has the ability to conduct electrons, we call this an electrolyte solution, and it's going to behave differently than something that cannot. So pure water itself is not ionic in nature. It has partial charges, but not full charges, so it does not have the ability to conduct electrons. If you throw a non-electrolyte solution in it, like sugar, for instance, and that's what they're throwing in there, you do not have the ability to conduct electrons. So you will not have any electricity that is formed. So if you put sugar in there, sucrose, nothing will happen. If you put in sodium chloride, you now have an electrolyte solution. So if you've ever heard of drinking your electrolytes with like Gatorade or Powerade, they're talking about putting salt in water. So to get those electrolytes, to get those charge carriers, you just take a salt and you dissolve it in water, and now you have mobile charge carriers, and those can conduct electrons. And in the case that we see here, this little picture, we now have a circuit, right? So we have the ability to form our complete circuit, and electricity can move between the solution and light up this light bulb. Okay. Now, we can have electrolytes in a couple different forms. We can have them as what we've already looked at, a non-electrolyte, or we can have what's called a weak electrolyte. So a weak electrolyte is only going to partially dissolve, so it only has a little bit of current. And then a strong electrolyte completely breaks down into ions and has a good conduction of electrons. So non-electrolyte, no conduction of electrons. And this produces a non-electrolyte solution when dissolved. So it'll behave just like pure water. With our weak electrolyte, there is some conduction of electrons. This partial conduction of electrons are going to come from a partial breaking down into ions. Okay. Now, our non-electrolytes, that's going to be basically all covalent compounds with the exception of acids and bases. So all covalent compounds or molecules except acids and bases. Our weak electrolytes are going to be weak acids and bases. And when we dissolve these weak acids and bases in water, we produce a weak electrolyte solution. Okay? And then our strong electrolytes are going to have good conduction of electrons. Okay? So these are going to completely break down into ions. And these are going to include ionic compounds. So all ionic compounds. Along with strong acids and bases. Okay. As a note, the strength of the acid or base is determined by how much it breaks down into ions. If an acid or base completely breaks down into ions, it's considered a strong or weak acid. Sorry, it's considered a strong acid or base. If a acid or base does not completely break down into ions, it's considered a weak acid or base. So let's look a little bit more at weak electrolytes. So these are going to be weak acids and weak bases. So they're going to have a partial dissociation in water. So this means we have some ions, some intact molecules. We show this like this. So this is carbonic acid. When we put it in water. We break this down into ions. We produce an H plus ion that's going to attach to water. So H plus H2O will go to H3O plus. So it's going to produce our hydronium ions. So this is one of our polyatomics. It should look familiar. And our bicarbonate ion. But the difference here is this arrow right here. This is an equilibrium arrow. Which means that we have substances on both sides of the reaction. So we have some intact molecule, some ions. But it's going to go back and forth. Your reaction is going to go both ways, and it'll stay that way. As a matter of fact, we can write this reaction in either way if we would like. Because it is an equilibrium process, both the forward and reverse processes are occurring at the same rate and at the same time. So we could write them either way. So if we start out with 1 mole of carbonic acid, at equilibrium, there will be less than 1 mole less than 1 mole of our carbonic acid, less than 1 mole of our bicarbonate ion, and less than 1 mole of our hydronium ion. As a note, we should have equal amounts of hydronium ion and bicarbonate ion. Okay, some examples of weak electrolytes or weak acids include acetic acid, carbonic acid, what I've just written, hydrofluoric acid, and then some weak bases include ammonia and ammonium hydroxide. So here are some examples of some weak acids and weak bases which are considered weak electrolytes. To ions. So there is no intact compound or molecule. So when we take something like sodium chloride, it's going to have a one-way arrow breaking down into sodium ions and chlorine ions when we put this into water. When we take something like a strong acid, such as hydrochloric acid, and we add water, we are going to completely dissociate to produce our hydronium ion and our chloride ion. So this will completely dissociate. We won't have any intact molecule left over. Okay, so this will be completely gone. So 1 mole of each of these substances will completely break down into 1 mole of the ions themselves. Okay, we can see the same thing if we take a strong base, add that into water, we produce our ions. As a note, the only time I added water into the chemical equation itself was for the acid, and that's because that's the only one where the water and the acid or the water actually plays a role. So when we break down hydrochloric acid, that H plus ion attaches to water. We don't have any of the other ions that actually make an attachment like H plus does, like our proton does. Okay, some examples of strong electrolytes are going to be all ionic compounds. And then some of our strong acids, HNO3, HCl, HBr, HI, H2SO4, HClO4, HClO3. Some are strong bases. These are going to be group 1 and group 2 hydroxides. Okay? Okay, so let's think about what happens in solution with our strong electrolytes. So if we have something like sodium chloride, it's pretty easy. If we start out with 1 mole of this, after we add it into water, we produce 1 mole of this and 1 mole of this. Pretty easy. So there'll be 0 moles of this, 1 mole of this, and 1 mole of this after it has dissolved. Something like magnesium chloride, when this dissolves, it produces 1 magnesium ion and 2 chlorine ions. So after dissolving, there'll be 0 moles of this, 1 mole of this, and 2 moles of this if we start out with 1 mole of magnesium chloride. Something like sodium phosphate. When we dissolve that, we'll produce 3 ions of sodium and 1 ion of phosphate. So again, we'll have 0 moles after we've dissolved here, 3 moles here, and 1 mole here. As a note, polyatomics are molecular ions, so keep polyatomics together. Do not break them apart. They are not going to break down into ions. They're going to break, the polyatomic itself will be the ion. Okay, that's everything. Hope you guys understand a little bit more about electrolytes, and I will talk to you guys in the next video. Bye.